Hello, everyone. I'd like to start by thanking you for attending my or tuning in to my talk here on long-wave, mid-wave arrays. Additionally, I'd like to thank the folks at IAF 2020 for having me here today. So I want to begin by briefly telling you a bit about my company, Materion. We're a global company with 33 locations and 2,700 employees. We have three distinct business units. There's the performance alloys, advanced materials, and the precision coatings, which is where the multispectral arrays are made. I want to welcome our newest partner here, Optics Balzers, who has now become a part of our precision optics family. Between the two sides here, we have over 150 years of experience and 160 different deposition systems. Those deposition systems cover a wavelength range from as low as 180 nanometers all the way up to 50 microns, covering many different applications, both commercial and scientific. We can make filters as narrow as 20 microns in width and as large as 1.4 meters. Materion's been in space for over 40 years, hundreds of different programs, thousands of different filters, covering a wide range of coating types and applications. If you look on the slides here, this is just a small sample of the hundreds of programs we've been involved with. So we've also been making arrays for over 40 years. Now, predominantly, those for sure have been mostly in the VIS and near IR, but there are many large government programs that have employed mid-wave and long-wave arrays for many, many years, including VIRS. VIRS has had long-wave and mid-wave arrays from Materion almost since the beginning. So let's get into a little bit more on the long-wave and mid-wave multispectral arrays. So there's two main type of arrays. There's a monolithic array and there's a butcher block array. The monolithic array is a single substrate that goes through multiple pattern, coat, and liftoff steps to get to the final spectral performance. Then it gets final sized and then a dark mirror mask is put on. For the butcher block array, you make the coating until you have what you want, then you dice it to the stick size necessary, then you assemble it and then put the dark mirror mask on at the end. For a butcher block assembly, which is really what we're going to focus on here because that's what you would employ for a long wave or mid-wave coating, you can build up to 150 different bands in one assembly and use many different materials within that same assembly. Bond lines are going to be about 15 microns to give you a very good band-to-band separation of OD5 blocking between each particular band. Everything we do when we're making an array is designed to give control, stray, light, and ghost. That goes from the coating design configuration, the materials you're using, and even the assembly techniques and the dark mirror mask that you use. So let's briefly walk through the different steps in making a mid-wave or long-wave array. First, you're going to go through the coatings. Once you have the coatings that you need, you're going to go through some sizing process. Then you're going to do the assembly. After the assembly is done, you do the masking. After the masking is done, you do the final sizing, and then, of course, the qualification. So for the coatings, as I mentioned, we have over 160 systems available covering a wide range of processes from IBS to IAD to E-beam evaporation. So for long wave and mid-wave coatings, typically you're going to employ E-beam evaporation because that's the best fit to get the spectral performance that you're looking for. When we're talking about mid-wave and long wave, we're talking between 2 and 15 microns. Each band that we make is custom designed to provide extremely high transmittance, steep slope, dense blocking, and we also can make narrow bandwidths as narrow as 0.2% in this wavelength range. Here are some performance results. These are measured results from filters that were made. You can see they all have extremely high transmission, steep slope, and very good band shape. Same thing here in the long wave. Extremely good transmission and slope. These are necessary to get the performance required from the multispectral array, and part of the reason why we do a butcher block technique in this area is you can run the coatings until you get exactly what you need from the spectral performance before you go into the assembly. So now that you have the coatings that you're looking for, you want to go into the sizing step. So we use specialty dicing equipment, which allows us to dice up to 200 millimeter wafers that are 10 millimeters thick. We can cut these wafers either straight cuts or angle cuts up to 45 degrees, which is what you would need if you wanted to build a parallelogram array and match the incident angle of the ray light coming in so that it would further reduce stray light and reflection. One of the key features of our dicing process is that the blades and the process we use gives a nearly commercial finish on the edge of each stick. What that does is not only does that minimize edge chipping, but it also gives us a really good surface to use for bonding purposes. Here's a couple pictures of some of the sticks that have been diced. You can see here on the top left that's straight out of the saw room and showing the different sticks on the same wafer. In the middle here, top right, you can see some 10 micron chips on a silicon wafer. And on the bottom, that's just a tray that we use to carry the sticks safely throughout the assembly lab until they get built into the array. So now that you're going to do the assembly, we do the assembly in a 10,000 clean room class 100 flow hood that's temperature and humidity controlled. All of the assembly and inspection is done under a microscope with using 2 micron accuracy. Here's a little bit of detail on the assembly. Is typically what we want to try to do is we're trying to maintain 10 micron coplanarity on the detector side. What that does is that gives a skyline effect on the backside. The skyline effect is usually in the range of 20 microns or so. Now, if somebody really needed a coplanar on both sides, we can and have done that before. It just adds a few steps and some complexity to the assembly process. You can see in the slide or picture in the middle here, it shows the opaque epoxy that we use to get that band-to-band separation. The diagram on the right sort of depicts what that band-to-band separation, how it reduces the crosstalk. The epoxy that we use is space qualified and meets all NASA and ESA outgassing requirements. So now that you have the assembly made, you want to put on the dark mirror mask to further reduce stray light and reflection in that transition zone between each individual band. We use a photolithography process and a PVD coating specifically designed to meet reduced reflection in the wavelength range that we're talking about. And in the bottom right here, you can see we end up with a very defined opaque mask covering all the transitions between each band. Then it goes back into final sizing using the same saws and techniques that were done to get to the stick sizes. And then of course it goes into qualification. Now the qualification, we do all of our qualification in-house except for the radiation test. We partner with a local university on that. Our qualification testing can be as simple as standard humidity, adhesion, and abrasion, all the way up to extremely complex thermal shock. We recently had a long wave array that had to go through 200 LN2 to hot plate dunks to meet its durability requirements. So in summary, we can make extremely high performing optical coatings built into an assembly of any number of bands. We can meet any type of qualification required and making a extremely robust multispectral array in the midwave and long wave range. So with that, I want to thank you all for your attention. Certainly what I've done today here is really just a brief overview. So you have additional questions or want to reach out to me on anything, please use the contact on the slide here. And again, thank you and have a great day.